Okay, thank you everyone for coming to this tutorial. I'm Alan, and I actually major in computer science, and I'm working closely with Professor Swati Kiran in Center for Recovery on a project and bringing this tutorial. So we'll start with an introduction by me and Manny, Caroline, and Claire, who will be presenting remotely, and we will bring some case studies of our projects utilize machine learning. And after that, we will have some time to discuss everything. And if you have any questions, you can feel free to ask. Okay, so let's get started with introduction. So the first question is, what is machine learning? I'll move it this way. Okay, so we all hear a lot about AI, machine learning, neural network, or ChatGPT kind of thing. Yeah, actually, so they are all kind of machine learning, and machine learning is a branch of artificial intelligence. That is a field of study that gives computer the ability to learn without being explicitly programmed. So the difference between machine learning and those traditional programming is machine learning is data-driven, while traditional programming uses explicit rules. So let me take an example. We're trying to build a spam email filter. So in traditional ways, we will set some rules. For example, if the email contains, for example, lotteries or gift cards kind of words, then it will filter as spam. But there could be some disadvantages. For example, spammers can change a few letters in a word. For example, change the L in lottery to number 1, and that will fool the filter. And if I'm a friend of yours and we're just talking about something about lottery, that could be filtered as spam email as well. So in this machine learning way, we can create a database of emails, and we label some of them as spam email and others as non-spam emails. And the algorithm will see what features are those in common with spam emails, while the feature does not appear in regular emails. And it can learn about the feature, and if a new email contains that feature, it will be classified as spam email. Okay, so that's the reason why machine learning. And another reason is that it can handle complex and large data sets. Some data sets are very large that it may contain gigabits or even TBs of data. And that would be hard to handle the data set by human. And so by writing a machine learning algorithm, it can deal with a large number of data and, of course, automatically predict new outcomes for new data. The last thing is that just like regular programs, it can save labor of people. We'll get to know more about it in case study. Okay, so there are actually a large variant of machine learning, and today I just want to include 2 of them, which is supervised learning and unsupervised learning. Of course, there are others like reinforcement learning, transfer learning, but that's out of scope due to time constraint. So as you can see in the picture, supervised learning contains data labeled as circles and crosses, while unsupervised learning, they are not labeled. And we cannot see we cannot have labels feed to the model. So supervised learning, the definition is given a training set consisting of inputs and outputs, building a function that maps new data on expected output values. So here the output is label and input is features. So considering the previous example of spam email, the features are for example, words contained in the email and the label could be spam or not. So that's a binary classification, 0 or 1. 0 means regular and 1 means spam. And there are majorly two kinds of supervised learning. One is regression and one is classification. Regression is that we want to predict a continuous value based on one or more variables. That could be, for example, predicting house prices, or like predicting the sick area in the organ. So some traditional approaches we often use and still popular now is like linear regression, ridge regression, and polynomial regression. So of course, like those neural network or transformer thing can also be used in regression problems, but actually they have a wide range of use. They can also use in classification, for example. So classification is that identify which of a set of categories an observation belongs to. So some traditional algorithms we often use is like logistic regression, support vector machine, or like KNN or K nearest neighbors. So logistic regression here, though it's named regression, but it's actually a classification algorithm. So come to unsupervised learning. So it involves training models on unlabeled data to discover hidden patterns or structures. So only features are contained in the data set, but no label. So which means the algorithm will have to find the patterns themselves. And one typical type of unsupervised learning is clustering. So we have, just like this figure here, we have two groups of data, and the algorithm will learn how to cluster this data into different groups. And there are also like dimensionality reduction. So in a very complex data set, we can have a lot of features. And it could be hard to visualize or interpret these features. By dimensionality reduction, we can reduce the dimension of features to maybe 1 or 3. So in this way, we can visualize them. We only keep those essential structures. And so it can simplify the complex data sets and make us easier to interpret. A third application is anomaly detection, which is identify data points that do not conform to a certain data pattern. So that can also apply to the spam email filter we talked about before. Instead of label the emails by spam or regular, we can ask the algorithm to group the emails in 2 groups, or we can ask the email to find some emails that are different from from other emails. So those abnormal emails could be like spam. Okay, so I'm not gonna like talk more about algorithms because there are too much algorithms and each of them is really different, and it would take a pretty long time to introduce you each of them. So I'll just begin with some principles. So we have training, validation, and test sets. Training set, which is very obvious, is used to train the model. And besides the training set, we need to pick some data from the whole data set as validation and test set. So validation set is used to fine-tune the model by adjusting those hyperparameters, which is used to control the training process. So these hyperparameters are defined prior to training and could be adjusted. So it could be tricky to apply the hyperparameters directly to the test set because that could be like biased. So test set must use to provide an unbiased evaluation on the final model feed on the training set. I'll go with a figure here. So we have underfitting and overfitting problems. So this is mostly for the training process. If we train the model too simple, we can see the results doesn't really fit the pattern of data. But if we train it too complex, it could be like overfitting. So if there's a point in the test set which is over here, the error could be huge. But actually, this point just follows this pattern. So and back to the validation set. So there's a problem that we can use some tricks to make the model fit the test set, which makes it seems the result very fancy. But we can imagine like this is not the training set, but it's the test set. So in this way, we use some trick to, for example, we just assign the values to these zetas. So it can shape like this, but in the for real data, it could be like make huge errors. So that's why we need to employ validation set. So if the model can run well on validation set, then we use it to feed the test set. So if it runs like this on validation set, but in the test set, the error is large, so which means there's some problem with our model. Okay, so after we have trained the model, and how can we evaluate them? So we can have like for different models, we have different performance metrics. For example, for regression problems, which in case you forgot is to predict a continuous value, we can use like mean square error. So it's used it's the real value minus the predicted value and take the square of it. So it's a square error, and we sum up each value and take the mean. So we can evaluate how far is the predicted value from the real value. And we can also see mean absolute error, which is rather than square, we take the absolute value. And for classification algorithm, we can have like accuracy. So it's 1 if you predict it right, and 0 if you predict wrong. And we can also have precision, recall, and F1 scores. So they're all evaluation metrics about classification algorithms. And we also have like other algorithms, for example, IOU score used in semantic segmentation and Siliho coefficient used for clustering algorithms, etc. So there are actually too much of them, and I just want to give you an insight about these algorithms and what types are they, what do they have, and later we'll be like in the discussion part. If you're interested, we can hands-on write some code for real model and use a toy data set. Okay, so later on, I'll start with my case project, which is actually not related to neuroscience, but this is my undergraduate thesis. So this is a detection of liver fibrosis with convolutional neural network. I'll start with the background. So liver fibrosis is an important symptom of development of liver diseases. So we can have some very common diseases like fatty liver disease or hepatitis, and liver fibrosis is a symptom of those diseases. And the most severe level of liver fibrosis is cirrhosis. So that can lead to like liver cancer, which is very severe and the second most death cause across the world. So abdominal CT scan can avoid harm to patients from invasive examinations. So just imagine like cut a hole in your tummy and grab out a part of your liver that could be very hurt. So we are currently using radiology CT images to examine the level of liver fibrosis. However, like the accuracy requires rich experienced radiologists that and also cost them a lot of time. So it could be like it may take them like several hours to diagnose the level of one patient, and which increase the cost of labor and also costs for the patients as well. So we're employing machine learning methods to interpret images and speed up diagnose and of course save labor for our radiologists. So this is kind of a very basic introduction of convolutional neural network. It can extract abstract features from images by convolution. So in the top image, we have a cat. And so these boxes are actually features in this image. And we can use convolution to extract this feature information from the image. And finally, we can produce a prediction. So in this example, each vertical line indicates the possibility of one category. So the highest one is tabby cat. So we can predict this image as a tabby cat. And we can also use convolutional neural network to make segmentation from an image. So this is the whole image. It has a dog and a cat. And so we are trying to extract tabby cat from this image. And after the convolution, the output of the network is a heat map of tabby cat. You can see on the right of the image, which is indicating the tabby cat is on the right of the image. So the data set we are using is abdominal CT images, which is 3-dimensional and annotated by radiologists. So these are the 3-direction size for one single image. And this is, and the green parts here annotated is the liver portion in abdomen. So in total, we have 99 3D images. Each has also indicated the fibrosis level of liver from 0 to 4. So the network we're using is called UNET. I don't know. It's actually a famous model for medical image segmentation. And the basic idea is to use convolution to extract feature information. But in the moment of extracting the feature information, the size of image is becoming more and more smaller, as we can see here. And so less spatial information will retain in the process of convolution. So this network also contains a upsampling path to reproduce the image to its original resolution. And so by upsampling, it can retain the feature information, which is more of like a context in the image. And it also concatenates the original image after like several rounds of convolution back to the upsampled image, which can combine the feature and spatial information in this higher resolution. So finally, the output would be the same resolution as the original image, and it would be like a map of 0 and 1, which here 0 indicates the non-liver area and 1 indicates the liver area. So our result here, like we use dice coefficient to evaluate the semantic segmentation. So it's calculated as this. So X and Y here, X is the real area labeled as yellow, as green in the previous slides, and Y is the predicted area. So we take the common part of these two sets and divide by the sum of these two parts, the sum pixels of these two parts. So it could be range from 0 to 1, which 0 means these two sets have nothing in common, and 1 means they're all overlapped. So here we have an average accuracy of 90%, average dice coefficient of 90%, which means about 90% of the liver regions are correctly identified here in the network. And the second step would be from the liver portion, we identified from the whole image, and we can use another convolutional neural network to produce the level of liver fibrosis, which is indicated in each image as well. So there are actually 4 levels here. You can just read them, but to be honest, I'm not going to show you the results because they're not good. That's why I didn't publish this paper. Okay, so that's a brief introduction of my case, and of course you can always ask me for more information if you have questions. Okay, so I'm going to invite Manny to present his case.
Thanks, Alan. Great job. So my background is as a speech language pathologist. So what I'm really interested in is using machine learning to answer some more clinical questions. Hence, my presentation will talk a little bit about the background of our clinical sort of problem, why we're trying to solve it, and what we're interested in extracting from what the machine learning models can tell us. So there are 2 sort of things that we're interested in. One is, do the models tell us things that are different from what we would anticipate from the literature? And 2, do the other things that the models tell us, do they align with what the literature would predict? So there are sort of 2 different things going on here. And this is why I label it an exploratory machine learning approach, is because we really didn't know what to expect in applying these models to these kind of data. So just to give you all some background, so I study aphasia and bilingualism. And aphasia is a language disorder that affects a person's ability to communicate, and it impacts approximately 1/3 of stroke survivors. And bilinguals comprise more than 50% of the global population. So an aging bilingual population will result in more cases of bilingual aphasia, and we should be anticipating that as a workforce and medical team. So there are a variety of cognitive linguistic treatments that are effective for bilingual persons with aphasia post-stroke. And we actually see benefits in the treated language alone, or also in both the treated and untreated languages. So this ends up becoming a question about saving labor, sort of like how Alan discussed, is if we can figure out what language is the most efficacious for bilingual individuals with aphasia, we're sort of saving ourselves some time and trying to work out what language to treat. So what influences outcomes in bilingual aphasia? Well, we can look at the literature in monolingual aphasia, So we know for certain that things like age, education, the severity of the aphasia, their residual cognitive processing skills, all these things affect treatment response. So how well someone does in responding to speech and language therapy. And then in relation to bilingual aphasia, we also know that some characteristics regarding their bilingual language experience, so for example, at what age they acquired that second language, that will affect outcomes. And we also know that the language of treatment will affect outcomes. So whether they're treated in their first or second language, for example. So treatment response in aphasia, much like you can imagine treatment response to many other kinds of therapies, is pretty complex and multifactorial. So it's actually a great opportunity to apply some of these machine learning approaches because they can handle such complex and large data sets. We've actually done this in a study in monolingual aphasia. And in that study, we also used some imaging data. But in this one, we're only looking at behavioral data in predicting response to rehab in chronic post-stroke bilingual aphasia. So this is really an extension of some of our previous work. So our objective was to use feature sets. So remember, if features are these different variables, so feature sets are things like groupings of variables that us clinicians label as falling into a certain category. We want to use different feature sets to build predictive models for treatment response. So I'm going to present two analyses here. One is our robust responders, so people who are responding robustly to therapy. So that's a 50% change in naming accuracy on words that we trained from pre to post therapy. And then a more traditional responder versus non-responder analysis in which we're just looking for a 25% change in naming accuracy on trained words from pre to post therapy. So a little bit about the ProCom trial. So this is just the paper introducing the trial, but it's a double-blind parallel randomized control trial in which we're using computational modeling to predict what language is going to be most efficacious for a bilingual person with aphasia. So I'm just going to present some of the overall statistics here as we just wrapped up this clinical trial. But as you can see, about 28 participants received therapy in Spanish and 20 participants received therapy in English. So in a way, we were able to look at this sort of question of what language might be most efficacious, thankfully, based on the distribution of the languages that the model was suggesting for us to treat people in. So just a little bit about the treatment real quick. So we have these 48 participants. A separate computational model is prescribing what language to do the therapy in. And the therapy itself is what we call semantic-based treatment for word retrieval deficits. So there are 6 steps to this treatment. The participants name or try to name an item. They get some feedback. They classify features about the item. Then they try to associate the item to something in their own personal lives or sort of a semantic association, hence the semantic basis for this. Then they verify some features. So they ask if it's an apple, if it's sweet, or if it's round. Then they try to name the item again. And then they produce a sentence related to the item. So that's sort of the course of treatment for 15 items for these 48 participants. And they only receive this kind of treatment for one of the 2 languages. So when we talk about robust treatment response, this is a graph of someone who shows robust treatment response. And what we really want to look at is this dark brown line. And what you're seeing here is that they're going from basically flat at baseline, B1, B2, and B3, to nearly perfect at P1, P2, and P3. So a massive response from baseline to post-treatment. And then when we think about our sort of traditional responder versus non-responder analysis, what we're really asking are who are the people who don't make any change at all? So when we talk about a more traditional or restrictive responder versus non-responder analysis, we're actually asking about non-responders, right? We're talking about who are the people who will show no change. Because a 25% change, if we look at the literature, is actually pretty marginal. So just to give an overview of the feature sets and features that went in, we had demographics. So we have 3 features here: education, age, and months post-onset. Bilingual language experience, which comprised 4 principal components. Their treated language severity, so their WAB-RAQ, which is a standardized, sort of the gold standard for aphasia severity in their treated language. The untreated language severity, principal component of their treated language assessment. Their untreated language assessment performance, again, as a single principal component. Cognitive assessment performance, so that's again one principal component. And then this feature set entitled patient language characteristics. So what this is coding are three variables, and one of these is particularly important. One of them is their first acquired language, so whether their language was English or Spanish, what language the treatment was delivered in, the treated language, and then whether this aligned with their first acquired language, so our treated in variable. So now to go on to the models and evaluative framework, and then talking a little bit about interpretation. So we wanted to sort of apply a pretty wide variety of different models. We wanted to cast a wide net. So we looked at different models like logistic regression and linear discriminant analysis, some ensemble techniques such as random forest and XGBoost. We also used an advanced classification method such as support vector classifiers, and also a neural network approach through the multi-layer perceptron. When we talk about evaluation, some things that we were going to look at were accuracy, the overall correctness, precision, the correctness of those positive predictions, recall, the coverage of correct positive instances, specificity, so the correctness of the negative predictions. And when you think about me saying negative predictions, you should really think whether the model is accurately predicting non-responders. F1, which is the harmonic mean of precision and recall, and Matthew's correlation coefficient, which is a particularly balanced metric, which is useful in these imbalanced data sets. So data sets in which your two different classes that you're classifying are very different in size. So to interpret these models, we can take a couple different approaches. One thing that we can do is simply count the number of occurrences of each feature set within the top performing models. So what we do is we run an algorithm that iterates over all possible feature set combinations, and that ends up with 255 different models for each one of these 6 models. So that's a lot of different models to look at. But what we can do is evaluate what's the frequency with which specific combination of feature sets are influencing model predictions. The other thing we can do on the level of individual predictions is perform a SHAP analysis. And this is a method to explain individual level predictions of complex machine learning models by understanding the feature or the influence of each feature. So this is like breaking down a recipe to its constituent parts and trying to understand which ingredients are the most critical to make the final meal. So when we move on to our results, what we see is that our support vector classifier performs particularly well on this robust responder analysis. So when we're trying to predict people who make a very significant response or make significant progress in treatment. When we see is a 0.894 of F1, we see a 0.895 accuracy. Again, that's the ratio of correctly predicted instances to the total number of instances. And we also see a particularly high precision. So out of those predicted responders, how many of those were actual responders? Now, when we look at the feature sets and their cumulative occurrences, what we then see is that demographics, this blue line, is really rocketing to the top. So that means that something in our demographics feature set is informing these models, and some demographic features, if not all of them, are heavily influencing correct or accurate predictions. Once again, when we look at the overall sets of models for our support vector classifiers, so on the left here, we're just the top 20, and on the right here are all 255. Again, we see that demographics is the feature set that is most prominently represented. So what we're looking at here is a SHAP plot, and the more red the circle is, the higher the value of that individual feature, and the bluer it is, the lower the value of that individual feature. And the further up the feature is located on this plot, the more influential it was in informing the model's correct predictions. So What we see here is that education. So there are two ways to read these, and I'll just read these in the way that I believe makes the most sense in how we're trying to answer the clinical question. So what we're seeing here is that education is associated with responder status. So higher values of education, more years of education are associated with responder status. What we see here is that lower severity. So the higher your AQ value is, that means that you're actually less severe. You have lower aphasia severity. So that's associated with responder status. So it's helping the model categorize people or classify people more accurately. And then what we see, and what we might expect, right, is that age, lower age, these bluer values are also associated with responder status. So far, all of this makes sense. Now, when we look at our responder versus non-responder analysis, and this is a more traditional, sort of more restrictive and sort of what we're interested in terms of sort of a bare minimum progress in therapy, we see that in terms of F1, our support vector classifier is once again sort of the winning or most superior model. And then what we see is that its accuracy is also highest. We see its precision is relatively high, although now you start to see that the XGBoost and some other models might compete in this area. And what we also see is that the specificity is relatively low, and it's relatively lower relative to, say, the XGBoost again. But what's particularly interesting about this question, this sort of bare minimum response to treatment, is that you can see that no model has a very, very high specificity like the last set of analyses. What we see here is that it's actually pretty hard for these models to predict the non-responders. So out of all actual, I should actually say non-responders. So out of all actual non-responders, how many were predicted as non-responders? So we then look at our feature set occurrences. So how many times these features are occurring in our top performing models. So when we look at our top 20 models, what we see is that both patient language characteristics and untreated language severity are two feature sets that are featured prominently in the top performing models. And as you can see, they're once again represented amongst the top performing models. So if you look at the x-axis, you can see that probably till about 150 or so, you can see that both of these feature sets are contributing heavily to the top performing 100 or so, 120 so models. But it's a little more ambiguous. And this means that this is a bit harder of a question to ask and attain an answer to. So then we can break it down and start looking at some of our SHAP analyses and our SHAP plot. So again, red values signify higher values, so higher numbers. And say the further up the feature is, the more important it is, or the more heavily it's weighted in the models. So what we see here is that untreated language severity is associated with responder status. So again, red values meaning higher. And then very interestingly, and remember, this did not show up in our robust responder analysis, whether the person was treated in their first language is heavily, heavily influencing whether the person is going to be classified as a responder. And the rest, I won't go through in the service of time, but as you can see, very similar patterns to our previous analysis, right? So we see that higher values of age, so people who are older, tend to be classified as non-responders, and so on and so on. So some takeaways of what we learned in applying these different machine learning techniques on these kind of data. So what we see is that there's some model consistency across analyses, and this is important for some of what we're interested in as a field, right? Is not only what can these models tell us, but are these models reliable? Can we sort of think about what models are best fitting our data? What's the best model that applies to these kind of behavioral data and these kinds of behavioral problems? What we see is that the support vector classifier consistently emerges as a top performer in both analyses, which is emphasizing its robustness and general applicability. So for those of you who are into, say, I know at least for speech and language sciences, support vector classifiers tend to perform really well in our data. And then our LDA model, while efficient, tended to lag behind the other models. Now, for our feature analyses, what we saw is that age, education, aphasia severity in both the treated and untreated languages, and what language participants were treated in, these things all influenced bilingual aphasia recovery. And this is, again, sort of anticipated by the literature, but we were able to slice the data in different ways to obtain different answers to a very similar question. So I will be around to answer more questions regarding this case study after we finish presenting. So yeah. So Carolyn is up next.
Hi, I'm Caroline. I'm a fifth-year PhD student in the Cognitive Neuroimaging Lab at BU. And I'm going to change tack here a little bit. So what Alan and Manny presented were, really nicely designed studies where they trained and tested these different machine learning models. My project is a lot more chaotic. So basically, I'm studying how human abstract reasoning, especially in comparison to artificial intelligence, and you're gonna see that I have a very rich and complex data set, and the past few years have just been me struggling to even find out how to look at this efficiently. So we're gonna, and all of it is like very much work in progress. So if you guys have any suggestions, please feel free to float them later. But basically the background for my project is who here has used ChatGPT and found it useful? Just a raise of hands. Yeah, quite a few. Yeah, so there have been multiple advancements in artificial intelligence technology in the past few years, most significantly the discovery of the transformer model. Which has allowed AI to become a lot more useful to us and a lot more approachable. But it still falls behind in human intelligence and how fast and flexible it can be. So artificial intelligence needs a really, really huge training set. And there's all sorts of problems with overfitting and underfitting. And I think recently there's just an article in The Atlantic about how there's a huge problem with pirated ebooks being used to train Meta's large language model. So there's obviously humans, we don't need to read thousands upon thousands of pirated ebooks to come up with a simple human-like answer. So in order to develop AIs that can reason better without having access to all that really large data sets, our goal is to first understand how humans are even good at reasoning and abstraction in the first place. And in order to do that, we're using a task set called the abstraction and reasoning corpus. And this is different from more traditional tasks of human reasoning in that it was built to actually evaluate AI reasoning. And it was first introduced through something called the Kaggle challenge. It's like a web platform where people can submit their different AI programs and compete in a challenge. And this task set was developed as a benchmark for artificial general intelligence. So basically, it's testing abstract problem solving with few-shot rule learning. So programs see a limited number of examples in order to learn a rule and then apply that and come up with an answer. And each problem in the task is novel and unique. Solutions are dynamically generated. So I'm going to show you what that looks like here. So we've adapted this task for human problem solving, and this is what my interface looks like. So to the left, there's two examples for these problems, this problem in particular, but most of the times people see between 3 to 5 example input outputs. And then from this here, they learn the rule, apply it to the test input grid, and then on the test output, they apply the rules to find the solution. They can click, select any of these 10 colors, and then draw out any shape they want by clicking on the pixels, kind of like Microsoft Paint. And then they can submit it, and the interface will show whether this was correct or incorrect. And solvers get up to 3 tries to get this correct, and they get feedback, and that's the same condition for both AI and humans, so we can kind of directly compare how they're doing on this task. And this is just an example of what the solution might look like. And the types of rules that people are supposed to, or solvers are supposed to extract from these differ. Some of them are more based on like pattern recognition. Others are based on more like counting and numbers. There's also like more directional rules. So I've taken 75 of those problems and done online data collection, first over Zoom with BU students and then on Amazon Mechanical Turk. So we have a pretty sizable data set now, around like 240 subjects across both phases of the project. And overall, the human performance on the task has been better than the best AI program that was submitted to the Kaggle challenge. The best AI got around 20% accuracy, whereas humans performed around 70% for MTurk and around 90% for the BU subjects. We are also doing a subset of these problems with eye tracking in the lab, so we're currently piloting that. All right, so we have all that data and it's all behavioral, but it's a pretty rich data set. So we have a wide variety of subjects and also of these different problems that all have a unique rule. And there's a lot of individual variability within subjects as to like how they perform and what kind of strategies they use, what kind of errors they make. And for each of the tasks, we have action sequence data that comprises of like reaction time and what kind of actions they're making, like the XY coordinates and color of the cells they're clicking in, but also like whether they're looking at the example or solving the task, or if they copied from the input to the grid, and all sorts of different things. So traditional statistical methods aren't really going to cut it to look at this data set. And what I'm kind of mainly interested in at this moment is from the human data is to sort out like the different strategies and errors that people make. And in order to do that, we kind of tried different types of machine learning methods on the action sequence data to kind of characterize how people solve these problems. Tried a lot of different things, none of them really stuck. One of them that we tried is K-medoids clustering. Another was like a more hierarchical clustering into dendrograms. And this is just like an example where my colleague Jing applied K-medoids clustering on this one problem, and it kind of separated out people into 3 different strategy groups. It kind of worked for this task where problem solving is more linear, but unfortunately it didn't really work well for others. And me and my colleagues kind of figured that maybe we're just looking at it wrong, because the action sequence is linear, but we hypothesize that the way people form these abstract representations of the task and apply that to the solving of the problems, it's more like in chunks and more hierarchical. So we decided to use a more graphical representation of the task data to better analyze it. And this is an example of that. These are 2 different solutions for the same task. And each of these nodes is like a click in a certain color. And the directional arrows are the order in which people made the clicks. So you can kind of see in one glance like how people solve this problem. And so we've been using this approach on a few different problems, and these are all like aggregated graphs. On the left, I'm just kind of showing the kind of like errors people make, and the blue is like more correct, red is less correct, and the size of the nodes are based on how many clicks people made. So you can see that people kind of correctly filled out these little chunks where they're supposed to. Oh, so this is the input output examples that they see, and this is the test input output. So this is the solution to the right they're supposed to get at. And then I've applied something called the page rank algorithm, which was originally developed as a way to rank web pages, because web surfing is a kind of action sequence if you think about it. And by looking at how people, like what route people come to land on a web page and where they go from there, you can kind of compute that and make a ranking of how important different web pages are to one web page. So that's kind of what I applied to these nodes. And in this graph here, you can see like the red one in the middle, it's by like comparing all the other nodes to that node and then kind of thresholding. So we end up with a cluster of nodes that are considered most important to that node. And this is a kind of unsupervised machine learning. And then to the right, I've just applied the color map here to this so that we can see whether these clusters have any relation to properties that we can observe, like objectness, directionality, or like the color. I'm just going to show a few more of these examples. This is another task where people, this one's pretty nice because you can kind of see where people made common errors here. And also compute like the importance of the nodes to each other. And another one here, this is the example I showed earlier. Yeah. And so that's what we've been up to so far. We want to take this analysis and combine it with the eye tracking data to see if that kind of clicking behavior has any relation to people's attention that we can track through eye tracking. And also ultimately our goal is to come up with a model of this kind of abstract problem solving. I'm working with my colleague Kwan Do in the Hasselblad lab at BU, who's also working like on a graphical model of our problem solving. So hopefully we can combine all of that data together and use those findings to find like some kind of hierarchical task representation in human behavior, and then apply that into this model. And that's it for me.
Any control?
Hey, can you guys hear me?
Yeah, very clear.
Okay. Okay. Sorry, everyone, I can't be in there in person, and also sorry if you can hear my yelling toddler in the background. Hopefully he'll settle down. Okay, so I am going to present, bringing it back into the speech realm and the speech pathology realm. I'm going to present on machine learning as applied to a connected speech analysis in post-stroke aphasia. So Manny already helpfully went through a lot of this background, so I won't kind of belabor the point, but just to give you an overall picture of the problem and why we're interested in machine learning. So as speech pathologists, we're seeing a patient who has some impairment in speech and language relative to their baseline, usually as a result of a stroke or any other sort of neurological injury. And a speech language pathologist is of course responsible for rehabilitating them back as best as possible to baseline. And we do this in a number of ways, through detailed assessment, through diagnosis, and also through treatment recommendations. And just to give you an idea of some of the challenges, so one issue is that this expertise and this time-intensive process is not available to all patients and not available equally to all patients. And also, a lot of the judgments we make as speech pathologists are essentially subjective, and we don't always know what factors go into that, and that can cause lack of reliability from clinician to clinician. So there's this general consensus that we could use more objective and especially scalable methods for efficient diagnosis, but that we still need as clinicians to be able to use these and interpret these. So I'll focus a lot of this case study on like interpretation, much as Manny did. Okay, so thanks, Manny, for the definition. So I'll kind of speed through this in the interest of time. So I'm looking at patients who also have post-stroke aphasia. I'm looking at people who are monolingual in contrast to Manny's project. So I'll skip over the definition there. Where it diverges a little bit is I'm using data from a large publicly available database called Aphasia Bank. And so this has over 200 plus, even more now, protocol standardized test results and speech recordings from people with aphasia. And I'm focusing specifically on the speech recordings. So looking at 1 to 5 minute recorded audio files of patients who are doing a Cinderella story retell using a wordless picture book. And I'm doing 2 kinds of feature extractions. From the raw audio, I extract acoustic measures. So you can see some examples of there. And from the written transcript, I extract linguistic measures. So that's just, those are some terms I'll be using throughout. And then over here, in terms of what I am predicting, it's an SLP diagnosis of whether someone is fluent or non-fluent. And this has to do with the ease of verbal expression. And it has some important diagnostic and treatment implications, which is why we're interested in that. And the results I'll be presenting today are looking at fluency in 2 different ways. They're both classification problems, but 2 slightly variations on it. So the first is looking at a binary gestalt decision. So this is the SLP just seeing the patient at the end of the assessment saying, I think this person is fluent or non-fluent. So using a lot of like behind the scenes reasoning, but nothing standardized per se. And then the second way is within the database, clinicians also use a 1 to 10 pseudo-ordinal scale, where 10 is the most fluent, 1 is the least. This is called the Western Aphasia Battery Fluency Score, or the WOB fluency score. And what we've done is then take that data and binarize it and use a cut point at 5 that's consistent with the literature. So just 2 different ways of thinking about binary fluency. Okay, and just asking the question, can we train a model to make accurate clinical judgments using only connected speech? Because this, again, would have implications for how scalable diagnosis could be. Okay, so just overview, 208 people with aphasia in this particular analysis. 2 ways of predicting fluency. You can see that depending on how we define fluency, we end up with more or less balanced groups. So that's just something to note. And then 147 individual predictor variables. So that includes 47 text-free acoustic, 84 linguistic, 7 that are kind of derivations of those. And then similar to Manny, we also are interested in demographic features and how those affect the model. So we've included whatever demographics there was available in the database. Okay, so general approach on the modeling. And I want to say, first of all, like we're sharing slides, and my whole approach is based on my collaborator Vijaya Kolachalama's labs paper, the Zhang et al. 2023 paper, which is in metabolomics, so quite apart, but has this awesome source code on GitHub. That's where I started to develop all these models. So hopefully that link works, and if not, please follow up with me. And so actually, I think Manny and I overlap. We're in the same lab, so not surprisingly, we overlap in the types of models that we've applied. So linear discriminant analysis, support vector machine, logistic regression, random forest, X gradient boosting, and the neural network, the multi-layer perceptron. I've kind of gone over these 2 different ways of predicting fluency that we're interested in. And then I have different combinations of features. So in one version, I'll run all the models with just the acoustic and linguistic features. In another, I'll include some demographic variables. And then something I won't talk about too much today, but I'll also had to do some feature selection because my features ended up being quite correlated with one another. Some imputation strategies as well, I won't touch on it in the interest of time, but because I had missing data, I did have to implement some imputation strategies. Sorry if you can hear that noise. And I tried different train test splits. So kind of what Alan talked about, I experimented with different train test splits. And the last thing I did is similar to Manny. I employed a SHAP analysis for interpretation of the individual features. So I'll go right into results here. So I just have these boxes to show you, like, in the interest of time, I'm not going to go through like each one of these things, but the bolded are like all the different variations that I toggled on or off. So in this case, we're looking at all models. I'm predicting the Gestalt clinician diagnosis of fluency. We're looking at inclusive of demographics, and you can see the various imputation and train test split details there as well. So just showing here, so what these graphs are just the area under the curve for the receiver operating characteristic and the precision recall plots respectively. Each dot, so for every model, I do a bootstrap run 100 times. So each dot is just one run of the individual model. And it just highlighting here that across all models, the X gradient boost was my best performing model. Although you can see that there's consistency across the models too. There's no one model that's like horrible compared to the other. So that was one interesting result for us. And so here I'm just going to show, much like Mandy did, I'm now focusing on my best performing model, the X gradient boost, keeping everything else more or less the same, and just showing the different performance metrics. You can see the accuracy, precision, all the same ones that Manny kind of defined for us. I'll just draw your attention for sake of time to let's just look at accuracy as we compare models throughout the next couple slides. So you can see we have an okay, decent accuracy here of 0.79. That's when we include all the predictor variables. That's this column here. When we take out the demographic variables, we don't see much of a decrement in overall accuracy in this case. So telling us that in this case, demographic features are not critically important to our overall predictive accuracy. That'll change for another one of our models. Okay, so now I'll present the same kind of figures, but this time predicting the second way of binarizing fluency. So this is when clinicians rated on the 0 to 10, and we cut point at 5. We binarized it based on that. Everything else is the same. Again, you can see, first of all, you see that the models are better overall, higher accuracy, higher area under the curve in this case. But again, X gradient boost is our best performing model in this scenario as well. So again, showing the same kind of thing. This is just showing with all the variables, including demographic and without demographic. And I do want to highlight one thing here is so our accuracy, as we saw from the other graph, is quite a bit higher than our first model, our first way of predicting fluency. So accuracy of 0.87. But a big decrement in accuracy when you take out the demographic variables in this case. So showing us that to predict this binarized score, for whatever reasons, and that's kind of field specific, I won't go into too much detail, but the demographics matter a lot more. So that's an interesting difference. And then just to talk about SHAP analysis, I'm going to go through these next 2 slides quickly, and then I'll put meaning to the various features. But this is kind of like a basic output of what you get from SHAP, so I did want to just share it. So we're going back to the first way of predicting, so the Gestalt prediction of fluency, fluent or non-fluent, no use of scales or scores. And when you run the SHAP, I did have to do some feature selection for SHAP to get rid of highly correlated variables. I can go into more detail in the discussion portion about that. But then we get the feature ranking, and it'll rank all features, and I've just displayed the top 10 here. And again, I'll add meaning to these features in 2 slides. And here's the same thing for the binarized WOB fluency score, just outputting all the top SHAP values and cutting it off at the top 10. And here's where we'll put it together. So just to bring it back, the first way of binarizing non-fluency is just the Gestalt decision. We see that non-fluent diagnosis is predicted fairly well. So it had the overall accuracy 0.79-ish. And it's specifically, so this will give you the direction of some of those SHAP values. So predicted by having apraxia of speech, so a positive, and that's like a sub-diagnosis of basically motor impairment. Motor speech impairment, shorter average utterances, slower rate, articulation rate in this case, more word errors and prolongations, fewer number of unique words and verbs per utterance, and then greater overall aphasia severity is also more likely to get you a diagnosis of being non-fluent. And the other thing we're interested in, the bolding is actually showing the overlap between these. So I'm interested not only in within each of these models, which are the top performing features, but across them, because in clinically speaking, this is the same construct. We should expect many of the same variables to be important. So you can see here, the most important variable is overall aphasia severity, and shorter average utterances, and so on and so forth. So everything in the same direction for the variables that do overlap that are bolded. but not everything overlaps. So we see some similarities, but not complete overlap, even though these are, the same construct of fluency, clinically speaking. So that was one interesting finding from this. I think we're still exploring, but so just, yeah, in the interest of time, I'll wrap it up here. We see that objective connected speech measures can reasonably approximate gold standard clinician diagnosis. That's kind of a relief. Again, our accuracy values aren't through the roof, but they're not abysmal either. So that's promising and gives us a reason to interpret the SHAP values where we wouldn't otherwise if they were performing abysmally. And this hopefully holds some promise for like resource non-intensive accessible diagnoses, because again, these are just audio files and the associated transcripts. I just talked about this, so yeah, that there's, when you measure the same construct but in different ways, some but not all of the features overlap, which is interesting, but the directionality of prediction for those features that do overlap is consistent, so that's reassuring. And then Manny kind of touched on this, but I think we both agree that SHAP analysis is really useful and helpful to add some interpretability to what could otherwise be considered like a black box model. So, and that helps us to align, are the features being identified? Do these align with prior literature or not? And without this, I think, at least I believe there would be little chance, that should be chance, not change, for clinical uptake, because people don't know what they're getting into and definitely won't use it if they don't understand. So that is it for me. Thank you. And again, sorry I was not able to be there in person today.
Okay, thank you, Claire. So that's basically all of our case studies, and so the tier 3 will be here for any open discussions, and if you have any questions about models, how to train the models, or like our cases, just feel free to ask or just come by.
Yeah, so does anyone have any questions about the analyses presented today, how you might apply it to your own data, different ways of thinking about using these models? So that's a good question. So I'm still figuring out what, and this might be helpful. Claire, you might be able to jump in as well, is, let's say we can use a machine learning model to quote unquote answer some sort of clinical question like, is this patient going to respond to treatment? And let's say that it's a successful model by most metrics, then what, right? So currently what we're trying to figure out is then what? So far we've interpreted the models. So I've basically double checked that the models make sense by doing the SHAP analysis, by checking, do these features align with what I would expect, or is the model mapping onto some bespoke set of features that somehow is producing a correct prediction? That's not what's going on. It seems like the models are actually able to accurately predict who's going to respond to treatment, who's not. So I think the tricky thing is, at least for where our field is now, like speech and language pathology, is that our data sets are relatively small. So as you might remember, I only had 48 patients in my data set, which is very, very small for machine learning analysis. And we didn't actually even go over this, but we use different testing and training methodologies to see what sort of might be the best approach to extract the most benefit from the limited amount of data we have. So my next steps, for example, are to sort of understand what I even did in the form of a manuscript present these results to our field, and then hopefully start the discussion as to whether these kinds of models can down the road be deployed in, say, a clinic where you can, introduce these different variables that we use in this model and see if we can actually, deliver something that benefits clinicians on the ground. So it would be a massive benefit if all you needed to predict whether someone was going to make a huge treatment response is how many years they've been educated, what's their severity in each language, and what their first language is, so we can align the treatment to their first language. So those are the kinds of things that are informing us. But in the field of speech and language pathology, the applications of these models are very, very new. Yeah. And much of the field is relatively unfamiliar with how these models work and what they're doing. So we're sort of like in the preliminary stages of introducing the field to what these models do and how they work, what benefit they might be to clinicians. Because I think I can only speak for my interpretation of how the on-the-ground clinician reacts to these things, but many people, even other scientists in our field, are pretty skeptical of how these models work and whether they would actually apply to a clinical situation. I don't know if you've heard that, Claire, but do you feel the same sort of? Do you have the same sort of perspective to sort of the
yeah, I heard your response. I don't think I heard the original question, but just guessing where in that realm it was. Yeah, I completely agree with your response, and second the skepticism too, and I think some of it for really good reason too, because it's not only a matter of like making sure we have features that we can interpret. That's definitely one piece that would help with the skepticism, but also I think there's skepticism about like how much, even in terms of like training to use the model, would these models actually be usable, even if we came up with one that was reliable, accurate, and interpretable? Are we going to successfully train people to use it? And also like there's still a lot of behind the scenes like feature engineering that can be quite labor intensive that like I can speak from my project that it's not like completely from native audio, and it's not as we're moving in that direction, but there's still some labor involved in some of these machine learning approaches too. So I think clinicians are rightly skeptical about that as well. So
I think different fields are in different stages of where they might deploy these kinds of models, and ours in particular is right at the beginning. But I know, and you might be able to speak to this, Alan, is like, I think radiology is probably one of the fields that's definitely further along in terms of interest in deploying these kinds of models.
Yeah, right. Because like computer vision is actually very much developed, and it's one of the hottest field in this area. But actually, my point of view is like, especially in medical area, those algorithms are just like assisting clinicians or experts for their judgment, but currently we just cannot depend on them to produce the results by themselves. Yeah. So currently, like, it can help experts to make some judgments or make decisions, but we cannot rely on them currently, especially in like medical area or those more important areas, especially related to human lives.
So in our field, Claire has used the biggest data set that I'm aware of. Insofar as, say, bilingual aphasia, I think our 48 participant data set is probably the largest data set of bilingual aphasia because it's such a niche area. But yeah, I mean, hopefully as time goes on, more and more people share their data, and it will help in the sort of development of these kinds of models, probably decades from now.
Why did you start using that
In speech pathology?
Yeah.
So I was a speech pathologist for about 4 years before starting my PhD. But I didn't know I was going to do a PhD. So yeah, I mean, I won't go into my life story, but it was an interesting field, and I thought language was interesting, and I was trained initially in linguistics. Yeah. Thank you for asking.
I think guidelines that sort of dictate the quality of your data set should have to know that it's appropriate for a machine learning approach. How do you know without sort of just getting the answer?
Well, yeah. So if we're like, especially when the data set is complicated and maybe contains a lot of features, like we may need more data. So generally, like for simple models, like not me, like, but they use, like, for example, those support vector machines, or maybe some decision trees, or simplest linear regression that would not require a lot of data. For example, like, I cannot give you an accurate number, but in my opinion, like, maybe 100 times of the number of features would be worth a try, or less, depends on the complexity of the data set. But when we're talking about like more complex models and complex data sets, like for example, ChatGPT, they use a lot of texts to train that model, maybe like everything we can get from the internet. And so that actually very much depends on your topic. Is the data set about text or about image or just numbers? It would be simpler if they're just numbers. Yeah.
So I guess part of machine learning techniques that I've always kind of sort of never quite understood is kind of how maybe like feature selection or feature extraction. I don't even know necessarily exactly what these terms mean, whether they're same thing, different things. And so it seemed, correct me if I'm wrong, but it seems like, Manny, for you and Claire, you have kind of like these a priori features going in you think are going to be important. But there may also be situations where you don't know what the features are going to be, or that you want to determine the features in a more like data-driven way. So I'm wondering if someone can talk kind of in general about what that looks like and what strategies there are for that step.
Well, about feature, that's actually quite tricky, like in the field of computer science, like for a same data set, like different selection of features can lead to very huge difference in performance. So generally, like for feature selection, that very much depends on case, but I just have some maybe general advice. So for example, you can try to derive more features if it's required. For example, you have a date indicated by year, month, and date, and maybe you want to see like what's going on in a same month within a year or a date within a month kind of thing. And so you can derive year, month, and date from the date feature. And also you may need to use like normalization or standardization to deal with the features. That's when they are in different scales. For example, one feature has a scale of maybe 0 to 1, and another has a scale of 1 to 1,000. That's that imbalance could lead to like imbalance in the parameters inside the model and lead to bad results. So it could be better like if you normalize the features, maybe like by dividing their dividing their standard deviation, so they have a 1 standard deviation, and or maybe like minus their mean, so they have a 0 mean, and so you will have a like -1 to 1 scaled data set. And if you do that to all features, that could be helpful.
Claire, do you have any, because I know you were working on this for a while, do you have any insight into sort of the feature engineering and selection approaches?
Well, no other than sympathy empathy that is really challenging and something I've definitely struggled with, and still doing so. But yeah, as was that Isaac who had that comment? Yeah, it's correct that I started with like a priori features basically. I did try to cast like a huge net, so there were features that I wasn't necessarily convinced would be important, and I thought, okay, the SHAP analysis will give more clarity to this. So I tried not to impose too much of a subjective judgment about what I thought would be important up front, and just cast like as wide a net as possible. So in my case, I used some like automated pipelines that extracted tons of features, and then I didn't do any selection as a first pass. But then I ran into the issue that when I went my first pass on SHAP, like I kept the top performing features were like different ways of calculating the same kind of features. Like they were mathematically non-identical, but they were, construct-wise kind of the same thing. Like for instance, calculating length of utterance by morphemes or words. So basically the same. And so I did have to then go in and try to do some sort of feature selection up front, and the way I chose to do it was to just take out highly correlated variables, because again, I didn't want to make too much of a judgment or look at their relation to the predictor at that stage. But I'm still not convinced, yeah, that's the right way or the final way I'm going to do it. But those are my thoughts at the moment.
Yeah, I would say my interpretation of this as a clinician is, at least if you're using these models in a clinical capacity, it's good to exercise some of your clinical judgment in curating some of the features that are going in. And it's also helpful to sort of use some data-driven approaches that also tell you what features you might want to consider retaining. And there are some data-driven approaches in certain like computational toolkits that can sort of rank order what are the features that are most heavily contribute to accurate predictions. But I think what makes it difficult is trying to meet halfway with sort of reality when you do academic research. So if you're planning to deploy this in a clinic, if that's the end goal, then it's not super feasible to say, I'm going to run such and such algorithm on a massive cluster, and it's going to tell me which features, and that run in itself could take hours and hours. Like it's you have to meet some minimum of like sort of this is feasible to actually do in a sort of clinical capacity. There are certainly papers in our field that explain sort of the possibility of using these kinds of models. What I think of is sorry for anyone who's not aphasia, but what I think of is like the 2017 Christina paper, where they used the stacked prediction to predict floppy two. But if you look closely, they're describing like this is how much work it went, like this is how many hours it took to train this model, et cetera, et cetera. So there's you have to find a way to thread the needle with what's sort of possible and realistic to do in clinical capacity, and also what you can just show theoretically.
Well, as we don't have much people here, so I just wonder, like, how many of you have hands-on experience with machine learning models, or so you like just heard of it but never use it? So my thought is like, I know it would be helpful to like maybe show you step by step to create a very simple model. Okay. So first of all, I highly recommend you to use Conda to manage your environments, so your computer won't be too messy. So first we use Google search and Conda, and here we can download it, and of course select your operating system, and after you install that, you can use your terminal here to, you can type Conda here to see, right? You can see a bunch of commands which can which you don't really need to know right now. So here you can see create is to create a new Conda environment. Let's say let's use the help command to print some help information. Like actually here you can see some examples. Create an environment containing the package SQLite. Of course, we don't really need SQLite. We can just use Conda create -n. So the n here indicates name, and we can just type a random name full and proceed. Okay, so you can see here to activate this environment, use Conda activate full. So right now you can see a full at the left of the command line, which means we have activated this this environment. And I suppose we can hit Python here. Okay, so when we hit Python 3, we can see a command line over here. And so we have our Python, and we need to install some useful packages. We type pip install, like at first numpy pip3 as well. And we wait for it to download. And as I introduced, like very simple model, we can just use sklearn. I hope I got it right. Okay, instead of just code text, I recommend using Jupyter Notebook, and we also install notebook. Okay, so we have notebook installed, and we can type here Jupyter Notebook. We need to install Jupyter as well. Well, um, something wrong here. Maybe I'll start with Colab. So just use Google to search Colab, and it will lead you to Google Colab, and you create a new notebook here. And anything you need is actually pre-installed. So the only problem with Colab is that you need to upload your data to Google Drive, which for some large data set could take a while. So we're just using, we can first import some packages. I started with two. So we click the play button here and execute this file, and we can create more cell here by clicking this. So a good thing about notebook is like you can run the code only the code you want, and you can print everything you want. So for example, I can create a variable here just by typing maybe x equals 1 and run it. And I can create a new cell here, just type x and run. So its value is printed down here. So it could also be easy to monitor the training process, as well as like when we're dealing with the data, we can easily like edit the data without influencing the previous one. So we can, instead of 1, we can use the NumPy, which is a very powerful library to deal with arrays and data. We can create an array, start from 0 and with 10, and have maybe 20 here. So run, and we can see what X looks like. So this is actually create 20 values in an array. The minimum is 10, and the maximum is the minimum is 0 and maximum is 10, and this is created in a linear basis, and we can also create a y equals 2 times x, and create a cell. You can also see y. Y is another array that the value of y is double the value of x. And create print x here as well. You can see. And okay, so we've imported sklearn and we want to like create a linear regression to map y to x, which means the 2 is the number the model should learn. So initially the model does not know like what this value should be. This is called weight, and usually weights are initialized as 0, and the model can learn from the data like what the weight should be. I need to look that up as well. You're always free to like search around the internet. Also, maybe use ChatGPT to get whatever you want. So I'm gonna search a little bit about document here. And as you can see, this is a class here, and all we need to do is from dot. This is the prefix, it's package. Just we can just paste it here. From this package, import linear regression. Okay. So here we can create a linear regression model named as LR. And we can feed it, which means train it with X and Y. So because linear regression is a supervised model, we need to pass the features, which is X here, and labels, which is Y here. Oh. Yeah, some value error. Okay, so it needs to be 2-dimensional. We need to make some reshape. Okay, so we have fitted the model with X and Y, and so we can create another test set. For example, we use this to create an array, and maybe let's say it contains values 50, 60, 70. And we want the linear regression model to predict our test set. We also need to use a 2-dimensional array. Okay, so here we have our value 100 and 120 and 140, which means our model successfully learned this number 2 from our training set. So for sklearn, it's quite simple. You just import the model you need, and you create an instance, and you feed the model with your training set, and you predict with your test set. And also you can, for all the models here, there's a score function. it also takes like our test set as input, and it can produce the score of our test set. So here it takes two arguments. The first is our test input, and the other one is our test output. Create an array like, we'll say 100, 120, 140, which is our test output is twice as test input. So it will output score with 1, which means we can see what function it used here. It's the coefficient of determination of the prediction, which means here is we can see like it's a y minus something. So we got a score 1 means it perfectly predicts the value. And we can like maybe make a little change here. It's not 100, it's 101, and we can see like it's smallly lower than 1, which means our prediction is a little bit wrong, but still good enough. But if we change it to a very different from the predicted number, for example, like 200, we'll see the number is negative, which means it's quite different from the predicted output. The real value is quite different from the predicted value. Okay. So we are using like no matter you're using like linear regression or sklearn also contains a various many models, like for example, there are linear classifiers, and linear regressors also a lot, and they are just linear model, and there are, for example, cluster models that have a lot of models here. You can feel free to use any of them, and just be sure to check the document, check what the input output should be before you apply the model. So this is quite simple. And when it comes to like deep models like convolutional networks or recurrent networks, that would be a little bit tricky. You need to use another package called PyTorch or TensorFlow to build your own model. That is not included in these libraries, maybe sklearn kind of libraries, because you have to like customize your model for your own purpose. So for beginners, like you can just use Colab to run some toy data sets and try them yourselves. Okay, so
questions? Or do you know of any other, say, websites or data sets that are good to practice on, resources?
well, data sets like actually for different purposes, there are a wide range of data sets. For example, like you can create your own toy data sets like this, and you can actually add a noise here. Like this, you have a mean of 0 and scale of maybe 0.1. And in this way, like you can see, you add a little noise on your label. And there are also like some data sets you can use, for example, for regression purpose, you can use Iris data set here. Oh, so this is actually for classification. You have like some features here. They are actually for, Iris, the kind of flower, and there are two kinds. Three kinds of flowers here, and they have different features, length, width, and so there are 4 features and 1 class. You can maybe try this one. They are all numeric. You can try this one for your own data model, because since there are like 3 classes, you can, if you are just trying a binary classifier like logistic regression, you can maybe put this is as 0 and these 2 as 1, indicating 0 means it is setosa and 1 means it isn't setosa, kind of thing. And there's I think sklearn provided some data sets, right here. And for example, California housing data set is like predicting the house prices. Let me see, it has 8 dimensions, and the target is a real number. Let's take a look. California housing data set. So it has its location, longitude and latitude, and we have a housing median age, which means the median age of the house owners within a block. The age of house, not house owner. So the lower means the house is newer, and the total rooms, total bedrooms, population within the block, and total number of households, and median income, median house value, and all right. So there are a lot of features here, and you can use these features to predict the price of this specific house. This is for regression analysis, and the Iris one is for classification purpose. And you can also explore like some digits data set here. So digit is actually some handwritten numbers, and it's good to use for like doing some image classification. This is the most simple one. We can also take a look. So this is actually a 8x8 grayscale image. This is quite abstract, but yeah, it's like this one. So there are like 10 categories here from 0 to 9, and you can train your self-model to identify each handwritten number, which number it is. Okay. So I hope you can maybe when you get home, you can write a little simple code to get yourself familiar with this package, and actually how it works is sklearn. In my mind, it's actually quite simple, just feed and predict, that's all. And this toy data sets could be good for beginners to just see, wow, my model worked. And when you're like utilizing machine learning techniques in your own research project, it could be a little bit more tricky, but the principles are always the same. And you can always feel free to contact me for advices from a student of computer science perspective.